Okay guys, good morning to everybody. So far in the previous classes we have seen basically what is known, clearly known. Yeah, all the physics of semiconductors that you can find in any book of semiconductors. There are many books, very good books about the topics we have been talking so far. Yeah? Since today and the 3 remaining days, we're going to see topics which are under debate. Yeah, so they are not things that are not very well known. I want you to grasp the at least some general idea of what are the main problems with these intergranular barriers and the conductivity in polycrystalline semiconductors. Something that is directly related to the way sensors work. Yeah, but this is not very well known, and people are arguing, and it's a topic regularly discussed in papers and in congresses, and we don't agree. So that is maybe that's the reason that makes this topic so interesting and attractive. Yeah, because things to discuss. Once everything is known, we have nothing to work on as researchers. So somehow this is a blessing that we have things to argue and discuss. Yesterday we ended up with a work function, a concept I want to stress because many people I think do not understand this well. Yeah, and again, the work function is the energy needed for an electron to escape from the solid, but to escape from the solid to what is called the vacuum level, and the vacuum level is not at infinite. It's very close from a macroscopic point of view, very close to the surface, right? And we found we discussed on the possibility of measuring the work function, which is something in principle difficult to measure, but we can measure it with something called the Kelvin probe method, which is a very clever method to measure the difference in work function between two metals. Yeah, and all we saw was for two pieces of metal. Well, the next step is to see what happens when we put in contact a metal with a semiconductor. Yeah, and that is called what it forms is what is named Schottky barrier. Yeah, after a guy called Schottky. That was his last name. In principle, we have a metal as we saw before. Yeah, this is the work function of the metal. This is the Fermi level of the metal, and we have a semiconductor. Yeah, and a semiconductor we define what is called electron affinity, chi. Yeah, they use regularly the letter chi, the Greek letter chi. This is the work function to the Fermi level. We are assuming we have an N-type semiconductor, and in principle we have no surface charges. That is, both the metal and the semiconductor are not charged, and this would be the situation. We are in the first column. Yeah, we are going to do this with this column. In principle, this would be the situation. This is the second picture, shows the situation when we put in contact the metal with the semiconductor. Yeah, before any charge transfer. But something is not well in principle here because the Fermi levels are different. Here is the Fermi level of the metal, and here is the Fermi level of the semiconductor. This is not in equilibrium. So to establish equilibrium, some charges have to go from the semiconductor where the Fermi level is up to the metal where the semiconductor is lower, right? So when that happens, electrons from the semiconductor start dropping into the metal up to the point in which the Fermi levels of the metal and the semiconductor are the same, at that point where we are in equilibrium. At that point, some region close to the surface of the semiconductor has gone to the metal, or at least went to this interface. So close to the surface of the interface between the metal and the semiconductor, there is a region which is called depletion region, because there are no electrons there. There are not electrons there, but we have charge. The charge due to the dopants. If we are dealing with an N-type semiconductors, those dopants are positive. Yeah, so we have here positive charge and the negative charge, which is at the interface. For that reason, since we have a positive charge and negative charge, we develop a potential as a function of x. That potential, which is this, constitute a barrier for the electrons that want to go from one side to the other one. Yeah, we have here a barrier to overcome, and that is called the Schottky barrier. Yeah, that appears in metal semiconductor interfaces. Okay, did you understand that? Well, this is the case when the work function for the metal is higher than the work function of the semiconductor. So if you go to books, most books are going to show these two cases. The next case is the case in which the work function of the metal is smaller than the work function of the semiconductor. If that is the case, look at this. Now the Fermi level here is higher than here. So the charge transfer is going to be from the metal to the semiconductor when we put them in contact. This is the situation immediately after the contact was made. So what happens is the opposite than in the first column. We have a region here close to the surface in the semiconductor with an accumulation of charge, of electrons. So now we have a band bending downwards. In this case, people say, this is written in many books, that we don't have a Schottky barrier, and this is named as an ohmic contact. This is called as an ohmic contact because the electrons can flow from the metal to the semiconductor, or from the semiconductor to the metal without any problem, because there is no barrier. In the other case, we have a diode behavior. You know what a diode is? A diode is non-symmetric. It has non-symmetric response. That is, the current is easy to run in one direction, not the other one. So here, if we have a negative potential here and positive potential here, we push electrons, and the electrons overcome the barrier. But we need to overcome the barrier. If we do it the other way, a negative potential in the metal and a positive potential in the semiconductor, electrons always find the same barrier. It's more difficult for them to overcome the barrier. The barrier is not reduced in height. So it's easy to go from here to there, but not from the left to the right. So it's going to have a non-symmetric behavior. So this is, in the literature, is known as a diode, the Schottky diode. Here we don't have a diode. Well, this is supposed to happen, and the difference, the reason for the barrier to form or not to form, one is expected to depend on how the work functions are. We have one case and the other one. Well, I must tell you that this does not happen for silicon, gallium arsenide, and many semiconductors using electronics. Many books present this as a solution to have an ohmic contact. Why do we want to have an ohmic contact? Because eventually, when a device is built, eventually we need contacts to go to the outside world, from the device. And we want those contacts not to introduce any electronic property, another extra electronic property. We want the current to flow freely, within the device. If we build a device and then we make the contact to introduce current, we don't want there to have an extra diode to be formed. We want an ohmic contact there. So what in principle all books say and those which are not aware of what is going on, is that what you have to do is to use a metal with a small Schottky and a small work function. In that case, the Schottky barrier is not going to form. Well, this does not happen for silicon. This does not happen for gallium arsenide, and for most of the semiconductors used in electronic industry. That is, a Schottky barrier forms anyway. Yeah. So, what is the solution to have an anomic contact? How do they do it? How the silicon devices are connected to the external world without having a diode in between? Do you know the solution? Good. Right. What people do is to heavily dope the surface of the semiconductor. And we make the contact. We are not going to avoid having the Schottky barrier. But since the doping is very high, the width of the barrier is going to be very small. And if the width is very small, we are going to have an easy transport through tunneling, yeah, from the metal to the semiconductor and vice versa. Yeah. Good. Fortunately, apparently, people say that for oxides, this is quite true. This works quite well. Yeah. That's for small work functions of the metal, yeah, or high work functions, yeah, the barrier forms or not, following this scheme, but not for covalent semiconductors. Okay. Well, there are tons of books and papers written about that. People essentially, I think that so far people do not agree. People talk of dipoles forming an interface, for example, the famous mix, metal-induced coupled states, and things like that. But interestingly, as the semiconductor has a more covalent character, the less response to these rules. And the more ionic the semiconductor is, the better response to this. Yeah? There's a famous, it came to my mind, a figure with the ionicity of the semiconductor versus how the barrier relates to the relation between the work functions. And amazingly, it's a very nice correlation. Yeah? Okay. So, what happens then at the surface of the semiconductor when the Schottky barrier forms? We have essentially a depletion region. Yeah, those electrons have been gone to the surface, to the metal, towards the metal. Essentially, as soon as a little the bottom of the conduction band, yeah, goes up, yeah, the density of electrons in the conduction band decreases abruptly because it depends exponentially, yeah, on the difference between the bottom of the conduction band and the Fermi level. Do you have in mind the formula? It's an exponential e to minus EC minus EF over KT. So this is called the depletion approximation, in which as this potential goes up, we should have a net positive charge appearing in this region. And this should go slowly, growing like this. But if we take something abrupt, it works quite well. It's a very good approximation. And this is called the depletion approximation. And now things are simple, because to get to obtain the field in the depletion region, we have to integrate this function, which is constant. The integral gets we have a straight line, and the integral of a straight line is a parabola, and this is the potential. So people agree in that the barrier, yeah, has a parabolic shape. Yeah, we cancel the double integration of a constant. Well, good. Next subject. regularly in covalent semiconductors, the surface presents surface states. That is, once you arrive to the end of the bulk, yeah, there is a region which is different because we don't have atoms on the side. The surface is we have a different situation. And in covalent semiconductors, regularly everybody agrees that there appear surface states, that is, states which are confined to the surface. And usually one way of doing it is like this. There are acceptor surface states and donor surface states at the surface within the gap. If these acceptor surface states were here in the conduction band, and these donor surface states were down in the valence band, wouldn't be a problem. That is, if they exist or not, it would be relevant from an electrical point of view. But being here, yeah, we have a problem. What's the problem? Donor states, yeah, if they are filled, they have no charge. Yeah. But as acceptor surface states, if they are filled, they have a net charge. Yeah, you know that difference between donors and acceptor levels. So if this is the situation originally, and we have here an N-type semiconductor, electrons from the conduction band are going to drop into acceptor surface state, and here we are going to have a Schottky barrier. Yeah, this typically happens in covalent semiconductors. The people working in ionic semiconductors, which are those used in sensors, do not agree what is the situation. Most people do not even consider surface states. There are some that are considering that they could have a role. So in principle, we are not going to have to take them into account in the field of sensors. Yeah, but keep an eye on that. Maybe they are there. Yeah. Okay. See what would happen if we have surface states of any origin. That is, they could be naturally happening because we are destroying, at the surface is destroyed, the translation symmetry. There are the crystal ends. That could be an origin of another origin. Suppose we have some surface states. That is a density of surface states there at the surface. If they're about the middle of the gap, which is what regularly happens with intrinsic surface states, and we have an intrinsic semiconductor, well, if the Fermi level drops about the middle of the between the donors and the acceptors originated at the surface, not much is happening. Yeah, the donors would be filled and the acceptors will be empty, so there is no problem, there is no charge there. That is the equilibrium situation. That is the equilibrium level. Yeah, there is no net charge at the surface. So not much would happen. What happens if we have an N-type semiconductor? Well, the situation is different because now the Fermi level is above the acceptor levels which form at the surface. And in that case, electrons would drop onto those acceptor levels at the surface up to the point we reach equilibrium. Well, the Fermi levels come into to the bulk and to the surface, but at that point we have a band bending, yeah, and the Schottky barrier forms. So this process can be present too if those states are intrinsic to the surface of the semiconductor, or they are due to the absorption of some external molecule or atom, yeah, from the environment. Here we have here a molecule. I'm thinking an oxygen. We talked of this yesterday. I'm going to repeat some things because I don't know if everybody didn't go to my talk of yesterday. So if we have a molecule, I'm thinking, or an atom, I'm thinking an oxygen, which is acceptor, is going to form acceptor levels at the surface, and this this species adsorbed on the surface. Yeah, we're going to have acceptor levels. We have here what is called the LUMO level. Yeah, for LUMO comes from last unoccupied molecular orbital. Yeah? This is the acceptor level. So electrons fall into those levels, and a depletion region develops, and we have a Schottky barrier formed. Right? So we are going to see this picture many times. Yeah? This is the situation. This is the surface of the semiconductor. We have the oxygen which was absorbed on the surface. We are considering that oxygen, the molecule of oxygen dissociates, yeah, into oxygen atoms. That's what people accept. That takes place at about 300 C, 300 degrees, which is a temperature regularly used for tin oxide sensors. So if this is taking place, electrons from here drop there to this level. The potential of the surface goes up, yeah, and things eventually reach equilibrium when the Fermi level is common to the bulk and the surface. Yeah. So now we see the problems with this, that is, the problems we have to solve. As you increase the pressure, yeah, what is the equilibrium here? Oxygen absorbs, oxygen dissolves. Yeah. From those rates, when those rates are the same, yeah, the surface is covered with some specific amount of oxygen. If the pressure is higher, we expect a larger number of oxygen absorbed at the surface. If the pressure is lower, the number of oxygen is going to be lower. The more oxygen we have in the surface, yeah, the Fermi level has to be lower, because if not, we're going to have too much charge on the surface. So to reach equilibrium, the Fermi level at the surface has to be lower. That is, has to be the distance between the bottom of the conduction band and the Fermi level has to increase. Yeah. If that happens, the band bending increases. So what do we expect? The larger the pressure of oxygen, the higher the band bending. You understand that? That's the principle of how sensors work. Okay. Here we have the same results explained for a more specific case in which we have two grains in contact. Yeah, these are the two grains which are in contact within a polycrystalline semiconductor. Within the grains we have conduction electrons. Here electrons can move freely. Yeah, and here we have a scheme of what's going on at the interface of the two grains. Again, to remember, here we have the depletion region, the charge at the depletion region of one side, yeah, the surface of one of the grains. This is the field, and this is the band bending. So what is happening here? Well, we have the Schottky barrier on one side, and we have the Schottky barrier of the other side. So between the two grains, we have two Schottky barriers, yeah, which are one close to the other one. In the literature they refer to two Schottky barriers back to back. Yeah? I mentioned yesterday, I don't know why back to back and not front to front. I don't know what the back of a Schottky barrier is, and what is the front. Which side is, well, it doesn't matter. That this is refer as that. It's back two Schottky barriers back to back. So now electrons to be part of a current within the polycrystalline material, they have to jump from one, yeah, to the other grain. So they have to overcome this barrier. And this is a limitation for the current. That is, within each grain in the bulk, there is no problem. Yeah, the resistance is very low. Yeah, the main contribution to determine what the resistance of the film is the barrier. So electrons have to overcome the barrier. Well, related to this topic, you can have tons of papers in the literature and in books. Everybody agrees that these are the basic mechanisms, but we do not agree on the details. Yeah? Here we see how a sensor senses. Yeah, with depicting I have depicted here a couple of grains. We are supposed here that we are in air with a lot of oxygen. So a lot of oxygen absorbs on the surface, ionizes, so you have negative charge at the surface. That negative charge is coming from the depletion region. So we have the depletion region, and then if we have the depletion region, we have a barrier. Yeah, this is from the surface of one of the grains. This is the absorption level of oxygen. Oxygen absorbed gives rise to an absorption level here in the gap. So the barrier forms, and if there is a reducing gas present, the reducing gas is going to steal oxygen from the surface. So in that dynamics, the final oxygen coverage is lower than in the case we have only air. Since we have a lower amount of oxygen on the surface, the charge at the surface is lower because we have a lower number of acceptor levels. As a consequence, since the surface charge is lower, we need to deplete a lower region and a smaller region within the grain. And if that is the case, the Schottky barrier is lower and the conductivity increases. That's fine. If you understand this, you understand how the sensor works. Okay, so far so good. Yeah, sure. Yeah, at lower temperature. People are working on that because to keep everything at high temperature costs energy. We have to heat up the semiconductor. The things do not, at least in tin oxide does not work at low temperature. And the reason for that is at low temperature, the surface is completely covered with oxygen. Regularly, the coverage is in the order of just a few percentage. So 2 or 3% is enough for the system to work. At low temperatures, all the oxygen covers completely the surface, and the system does not work because from a catalytic point of view, it becomes poisoned. Yeah, all the active sites are occupied, and you cannot produce a reaction for things to change. This is what happens at low temperature. So for these devices to work, they have to be typically at 300 C. But people are working and looking for some semiconductor that works. The lower the temperature, the better. And if it works at room temperature, it would be great. We don't have to. We would not need a heater there to keep the sensor, and the right temperature. Okay. Yes, please. What would happen here if at low temperature? That's the question. No. Yeah, this is not a metal semiconductor junction. This is a semiconductor junction. It behaves like a Schottky barrier, but this is not metal. We don't have a metal here. We have a contact between two grains of the same semiconductor, right? Was that the question? I mentioned before what the Schottky barrier was, because all the theory for this thing is based on Schottky barrier. Was that? Yeah, not the metal. Yeah, we don't have a metal here. Good. Well, things become more complicated. So I'm going to teach you things that people do not agree well. Let's suppose we are at 300 C. What oxygen does? And people do not agree on this. I took this equation from a book, from a guy I agree with. We have oxygen here in the gas, in the environment. The oxygen can absorb on the surface. That oxygen absorbed on the surface can ionize, can have one charge, can have two charges. Yeah? But not only that, that oxygen which is in the surface, it can diffuse into the bulk, yeah? Charge. And maybe it can become part of the lattice. Yeah, if this is happening, you see, the density of where this goes into the lattice, it goes to a vacancy. Previously we had an oxygen vacancy, and now this oxygen coming from the atmosphere is filling that vacancy. If that is happening, the dopant concentration is going to be smaller, it's going to be reduced. We are going to have a lower number of oxygen vacancies, so the donor concentration is going to drop. Something that does not happen regularly in people working in electronics. People who work in electronics deal with substrates, original. They have a doping, and that doping is constant. Yeah, it does not depend on what I do. Well, in this kind of semiconductors, ionic semiconductors, in oxides, this is under debate. Not everybody agrees with this taking place. Yeah. But in this case, I'm not the only in the world saying that this could happen. Yeah. And also people agree that the current through the coming from one to the other one is a thermionic current. And I think already mentioned that maybe we have another contribution, which is a tunneling current. So all these basic questions are not definitely answered in the literature. So one work we did in our group for years, we're trying to show if this is taking place or not, could take place or not. We found that it happens. I will show you now. Well, what happens when we apply to a barrier potential? Yeah, people don't agree also even on this, where the voltage drops, and the left barrier or the right barrier, here to say one or the other one. Well, people don't agree how that potential, applied potential, is distributed. Yeah, in principle, you think that the bottom of the conduction band here we are applying the negative potential on the left and the positive potential on the right. We think that the bottom of the conduction band on the left goes up and the other goes down. Yeah, and that facilitates the current over the barrier. But exactly how things work, people do not agree. In principle, at the beginning, as if the applied potential is very low, we are going to have two capacitance. You know the capacitance of the Schottky barrier. Yeah, as we apply the voltage, the amount of charge in the interface reduces or increases, and that is the behavior is that of a capacitance. So if we apply voltage and that voltage drops in the inversely, a diode, the diode which is inversely, we have an inverse potential applied to it. Yeah, in that case, we are going to have the capacitance due to one Schottky barrier, and that is known. And there is a technique usually done to calculate the barrier heights and so on. But if the voltage does not drop completely on the in the diode, which is inversely, yeah, with the voltage in inverse, the results can be whatever they want. Yeah, this is a typical, very used technique, but I think it doesn't work well. So here we have the Schottky barrier again. Here I wrote some details related to the total charge, the field, yeah, and the integration of the field, which give us the potential. So we see here the exact relations of the band bending, which is Vs, with the width of the depletion region and the dopant concentration, yeah. And if we have a double Schottky barrier, back-to-back Schottky barrier, we are going to have this barrier. Most people in the field consider that this is the main current, which is called the thermionic current, that is electrons jumping over the barrier. This is a new contribution. This is my contribution to the field. I calculated the possible current through the barrier, yeah, and see what could be the consequences of that. I have been arguing with many people who are well known in this field. They told me I was complicating the model, and I said I'm not complicating the model. That is, this is nature. Nature works like that. I'm applying basic quantum mechanics and considering the dopings you are considering, you are accepting, and the barrier heights you are accepting. Tunneling is unavoidable. Yeah? It has to happen. The calculations are not simple, but are not so complicated either. If I could make it, I'm not a theoretician, I could make them. Others with better abilities for this type of things are going to do it too. So the electrical transport in the Schottky barrier can be of two types. It can be electrons jumping over the barrier or through the barrier, yeah, tunneling through the barrier. So we have two contributions. This is the thermionic contribution, which I think you know. I will show you how this is derived. It's not easy. Maybe you have done it sometime in some course. But the current is proportional to an exponential, which depends on the barrier height. And if this is complicated, this is a little more complicated. This is a tunneling contribution. And the tunneling contribution, look, is an integral. Why an integral? Because we have electrons from the left coming, yeah? Maybe you have calculated in quantum mechanics the tunneling effect for a barrier for a specific energy, that is, in a specific kinetic ratio of the electrons coming from the left, and see how much of those can tunnel through the barrier. But here we don't have a specific energy. Electrons come to the surface with a Fermi-Dirac distribution. So you have to integrate to take into account all the electrons that are coming, yeah, are impinging the barrier with different energies and in different amounts. That's why you have to make an integral. So the integral has the TE is, this is transmission probability through the barrier, which can be calculated using quantum mechanics. And f of AE is the Fermi-Dirac statistics, saying how many of this, how many electrons I have as a function of energy, right? So, is this scary? No, isn't it? Well, let's start with thermionic current. What is the current coming from the semiconductor? Yeah, this is done for a Schottky barrier, which is a semiconductor metal interface. But essentially, when we do it for a double Schottky barrier, all we have to do is, yeah, to write down a symmetric potential. But I'm doing it in this case, this manner, because it's typical in the literature. So, to calculate the thermionic current, we have to integrate, take into account all the electrons which are from the Fermi level plus the Schottky barrier is from here to infinity. All those electrons, they have energy above the barrier height. Yeah? And you remember that the density of current was the charge times the speed, the velocity of the electrons, and times the density of carriers, n. But the problem here is that n, that is, those electrons arrive to the surface with different energies. So this is the reason we have to integrate. Yeah? We have integration. The number of electrons can be found in this way. N of E is the density of states. F of E is the Fermi-Dirac distribution. And making this, we did this before for this is the density of electrons as a function of energy. But this is the density of states. You have to multiply by the Fermi-Dirac. Well, and we have to make the mathematics. I'm not going to go into much detail. Eventually, we have to plug in what this difference is kinetic energy, and we have to calculate how many electrons we have, yeah, as a function of the speed. Integrate all this and get eventually what the current, the thermodynamic current from the semiconductor to the metal is. We have this constant A, which is called the Richardson constant, which depends on all constants known. And T is the temperature, and this is the Schottky barrier. So that the total charge jumping from one side to the other is lower exponentially, yeah, it decreases exponentially with the barrier height. Yeah? And this is what people accept. Well, thermionic field emission is called to the current which goes through the barrier. Yeah, I follow a very old paper from 1969 of Crowell and Rideout, and I consider the parabolic potential. And to calculate how much current goes from here from left to right, you can use the WKB approximation. I hope you have seen that in quantum mechanics courses. So the probability of transport, yeah, from left to right goes, yeah, as a function of this alpha, which is a function of the difference between the potential and the energy of the electrons. And then we have to make this integral to calculate the probability of, yeah, going from left to right. So alpha of x has this form. We have to plug in this in here, and we have to make this integral. Yeah. Fortunately, this integral is in tables. You can make it. You see the solution is not so simple, and eventually we get what the transmission probability is. Yeah? And depends on all this. See, that depends on the energy. Yeah, the energy of the electrons. And all the electrons do not have the same energy. That's why then we have to integrate. Yeah? So if you make the calculations, to simplify the calculations, you take a Boltzmann distribution instead of the Fermi-Dirac distribution, which is quite valid if because the Fermi-Dirac distribution for energy is not far away from the Fermi level up, it behaves as Boltzmann distribution. So eventually the total current, you have to integrate all the electrons, yeah, impinging on the surface, multiply by the probability that they can tunnel in the barrier. You understand that? Let me come back. You understand that when we are here at low energies, we have many electrons because of the Fermi, yeah, because of Boltzmann, we are using the Boltzmann distribution. But the barrier here is wider. In the upper part, we have a lower amount of electrons, but the barrier is easier to be overcome. So if you analyze the integrand of this integral, most electrons, depending on the temperature, but essentially you're going to have something like this. These electrons are going to overcome the barrier about the region in between the minimum of the maximum, yeah, of the barrier. Because we have two competitive functions. On one side, the higher the energy, the lower the number of electrons want to overcome the barrier. And the higher the energy, it's easier to overcome the barrier, to tunnel the barrier. Okay. So this is the number we have to calculate, the formula we have. And if we don't have a barrier, we are in a situation of flat band. This will be the situation, and then T of E would be 1, and we can integrate this. Typically in the literature, they define this constant is 0, 0, which depends on the doping and the permittivity and effective mass. So eventually, I don't want to bother you with this. We have this equation which relates the density of current as a function of the current if there were not a barrier at all. And here we have the formula, which cannot be evaluated just with a calculator. We have to make a program in the computer and calculate it in that way. Maybe that's the reason people don't like it. They have to work a lot. Okay, after all of this, we made a lot of calculations, and we found that regularly the situation is that the main contribution to conduction is due to the tunneling current, not the thermodynamic current. So people did not like that when we arrived at that conclusion, because everything was in the literature was essentially wrong. So for that reason, people did not believe us, what we were saying, even though we are not creating nothing new. We are applying things which are in the books. So we tried to show experimentally this was correct, and that was the challenge, to show that what we are saying was correct. So this is a typical. But typically we create a sensor. We have here the substrate, and the substrate is conductive, but with a laser we separate two sides with this shape. So then we paint the surface with a polycrystal, with a film, and we put that film here within the chamber. This is created with the computer. This is not a picture. So we have cut here the oven. This is an oven. So we put the sensor here within the oven, and here there are gases, that are entering. It has to be some exit someplace. I think it's here. So in that way we control the gases which are in the environment and the temperature. Okay. What is the typical response we found for our sensors? That we found immediately that the resistance of the sensor changes abruptly when we change the amount of oxygen in the environment. If we inject oxygen in the environment, you have a situation of vacuum. We say vacuum, but vacuum, for people working in ultra-high vacuum, this is not vacuum, but it's about 10 to minus 3, 10 to minus 4 torr. You inject air in the chamber, the resistance from very low value jumps, to a very high value. You run vacuum again, the resistance decreases. This is a typical response of the sensor under the pressure of oxygen. So the resistance abruptly changes, and if we pump out the oxygen, the resistance abruptly decreases. Well, this is a typical sensor, commercial sensor. Yeah? In the commercial sensor, you have on one side, the sensor is here. This green stuff is supposed to be the sensor. We have an interdigit contacts here from one side, and the other side they build here a resistance for heating. Yeah, and all this is within a commercial sensor. We here have a detail of how we make contact with the sensors we made. So this is usually very thin. It's very thin because we need that the gases can diffuse there. Yeah, that's another reason to have a high temperature in working with these devices. Okay. So some first results we found that there was no answer in the literature to these results. If we run things at lower than 300 C, we have 280 C. We put some, from vacuum, we go into air pressure, introduce air in the chamber, and as we saw, the resistance increases. But we saw something here which was suspicious. It seemed that the resistance wanted to decrease. So we increased the temperature, and the effect is even very clear now. Yeah, the resistance increases, but then decreases. And the higher the temperature, the stronger the effect is. Yeah. In several meetings with other scientists, we asked them what could be the reason for this. And the answer we regularly received was, well, there are many things that could happen at the surface. Who knows? It's not very important. Well, for me, I think it's important. Let's see why this is taking place. Yeah? Well, the fast initial increase in the resistance can be expected. As we saw, oxygen absorbs on the surface. There are created ions. Yeah, the acceptor levels, they are charged, and the intergrain barriers increase and the resistance increases. Yeah? And both increase, the height and width of the barriers. The later decrease of R. An increase in resistance is expected with exposure time that the decrease is observed. What would you expect? Well, as time is passing by, the system maybe has slow processes, and eventually it needs some time for the total amount of oxygen to be absorbed. Well, if that is happening, the resistance should increase continuously. It should be monotonically increasing, reaching steady state slowly. But for temperatures above 280 C, we observe a decreasing, not an increasing. Well, so what we propose? We propose that could be a reason for that could be an internal diffusion of oxygen. That oxygen was somehow diffusing. The higher the temperature, the easier it was for the oxygen to diffuse. And if the oxygen isn't diffusing, it will kill, annihilate oxygen vacancies. And if the oxygen vacancies are annihilated, the doping becomes smaller. And if the final doping is smaller than the initial doping, the depletion layers widens. You see that the lower the doping, the wider is the depletion region. And people said to me, but we don't care. The thermionic current is not going to change. Yeah, the thermionic current is going to change, but the tunneling is going to change. Because the narrower the barrier, the higher the current. If I'm making a barrier which is wider, the tunnel is going to decrease. So, interpretation. Schottky barriers are assumed. We think that they're forming barriers of the Schottky type. Yeah, the Schottky type. First, there is a change in barrel height and width. More oxygen on the surface, the barrel height increases, and the depletion width increases too. Second, change in barrel width due to oxygen diffusion. The barrel height essentially does not change, but since we have diffusion, the barrel width is going to change. And we have another problem too. If the grains are of intermediate size, it could be that in vacuum we have barriers with a region in the middle of the grain, as we saw before. But if the grain is not very high, as the barrier increases, could be that there is no room to have a bulk region, yeah, and the whole grain could be depleted of electrons. If that is the case, the mechanism that we are mentioning for conduction, this could be a completely different one. We are not having Schottky barriers in the regular idea that you have a bulk, the barrier, and electrons have to go from a bulk region to a bulk region. So if that is the case, the mechanism of conduction are going to be different. So barrel overlapping could occur, could take place. If that is happening, yeah, the resistance could decrease. It would be easy the conduction. And if that is the case also, we cannot talk of capacities of a barrier because we don't have essentially a typical barrier. Yeah? The capacitance of a barrier is due to that you are applying a voltage and then the depletion region increases and decreases. But now the depletion region is the whole grain and it's not going to change. So the capacitance is going to drop. Yeah? And if you make some numbers, see the depletion layer, the depletion width for a one-dimensional model has this form. Yeah, we have here. It depends on the barrel height and depends on the doping. And a typical value, if you plug in some reasonable values, you get about a depletion region of about 25 nanometers. But in 3 dimensions, things are not exactly the same, and essentially the depletion width are larger. Yeah. So, and typically people were using at that time when we were running these experiments grains of about 100 nanometers, which is exactly in the limit where the grain can be completely depleted of carriers. So here we have a scheme of what we thought was going on. So essentially, if we have large grains, yeah, or a high concentration of donors, we have a central region of the grain which has a bulk character, and the barriers close to the surface. Yeah, if for some reason the dopant decreases, yeah, the width of the depletion region is going to increase. We are going to have some bulk properties in the central part of the grain. But for small grains or for low concentration of donors, initially we are going to have a situation like this with very small region with bulk properties, and if we have indiffusion and we have for this reason we have a decreasing of the doping, and consequently the width of the depletion regions increase, we're going to have this situation in which the whole grain is going to be depleted of carriers, right? Okay, so this picture again, yeah? Could this be explained what we observe, just considering that everything takes place at the surface? That is, could be that the barrier height changes depending on pressure, temperature, time, and size of the grains? Well, people in the literature believe that this is possible. We think it's not possible. So we run out some experiments. This is photoemission. Yeah? Photoemission, this is a general wide scan and photoemission for 2 types of samples. The samples were treated in oxygen, at high temperature. So the doping is very low. Why? Because we allow the high temperature and oxygen can diffuse into the grains, killing, annihilating oxygen vacancies, so the doping is low. And these samples were prepared in a different way. We introduced in a preparation chamber, we introduced some hydrogen, yeah? And the hydrogen takes oxygen on the surface, yeah? So we are expecting these samples to have a much higher dopant concentration, that is, much higher density of oxygen vacancies. So the samples were essentially the same, but in this way, preparing with oxygen or an environment with hydrogen, we were changing the dopant concentration, that's the amount of oxygen vacancies. But essentially, the samples were the same. If you look at them, they're about the same. Yeah, are you usually have been using photoemission, the XPS technique? No. Yes. Okay, I expect so. Okay. Well, so the samples were essentially prepared in the same way, but after the preparation, we did this. What I have just told you, that this were maintained. Here's what we call the sample O2 was maintained an hour at 380 Cs in air, and instead of that, the sample which we call SH2 was maintained for an hour at 380 C in nitrogen with 5% of hydrogen. You could ask, why not more than 5%? If you put a lot of hydrogen there, essentially the oxygen in the sample disappear. You end up with tin, metallic tin. Yeah, we want to take some oxygen, but no, not too much. So we're going to change the sample from a semiconductor to a metal. Okay, so we ran some. We run some experiments. Yeah, measuring the resistance at different temperatures. Yeah, so we go. For example, the hydrogen treated sample, the white triangles, we were going up in temperature, and then we were going back, and it was quite reproducible. Yeah, and the conductivity was very high. And instead of that, the oxygen treated sample, we go to this temperature, and we come back, and it was not bad, but it was not quite reproducible. And it was amazingly different was the resistivity. Look at the resistivity here are very low. This is logarithmic scale. The resistance here is much lower than here. Yeah. So what would be the answer for the regular knowledge? Well, they would say, okay, you treated the sample with hydrogen, and then you alter the surface, and now your Schottky barriers are smaller. Yeah, and that's why the conductivity increases, because the intergranular barrier has lower height. Well, the fact is that samples, when you run XPS, the samples are under vacuum, under any atmosphere, are the same. So if there is a change in them, it's internal, it's not external. Yeah, but they told me that no, but maybe when you did the treatment with hydrogen, the surface was altered, and that did not change. Well, okay, let's go on. This is the sample that was treated in oxygen, and we initially, what I saw was up to a temperature about this value, not very high. If we went up to, say, the order of 300 C, and we come back, see that now it's completely different there. Yeah, it's not reproducible. The result is completely different after the heating and the cooling down. Yeah? And we thought, what can it be? Why the conductance is increasing? So somehow it appears that some oxygen from the sample could be dissolved, get out of the sample. Yeah? The sample is always under vacuum. Yeah, very low pressure. Oh, I put here the our software to just to take a look how, yeah, well, how they are. Yeah, all this is metallic, and we make contact here and here, and then we paint the whole thing with the film, and electrons have to go from one side to the other one. Yeah? Okay. Well, we have to remember how photoemission works. This is the situation, yeah? The general situation. When we have band bending, the internal levels also follow the band bending because it is an electrostatic, yeah, potential. The whole thing goes up or down. So what happens at the surface, yeah, if we have or not band bending, is going to reflect in the binding energy when we run photoemission. You know that. That is, as this level goes up, we have an internal, yeah, an internal level also follows the electrostatics of the system. So the position of the core levels measured through photoemission is going to change according to the band bending, right? So we measure with photoemission the position of tin oxide, of tin, the 3D level, yeah, for both samples. And essentially we found almost no change in the position of the tin 3D. What is that meaning? What is it telling us? This is telling us the band bending is similar to in both samples. Yeah? Similar binding energy is observed, indicating that the barrier heights do not differ significantly between the two types of samples we prepare. So the band bending is about the same. If the band bending is about the same, the conductivity should be similar if we take a thermionic model. Yeah? If the conductivity through the thermionic, yeah, current and the barrier is the same in both samples, yeah, the conductivity should be the same. There is a small difference there, but it's not enough to justify the measurements. So what is this telling us? The thermionic current is not enough. Yeah? Okay. Do you understand so far what I'm telling you? Look at this. The conductivity here is much, much higher than here. This was a sample treated in hydrogen. This is a sample treated in oxygen. Yeah? If the current were thermionic, and since the conductivity should be the same, you have the same barrier height. And this is what we measured with using photoemission, that the barrier heights were about the same. So the conductivity should be the same. But we measure very completely different conductivity. So what is the reason for that? Well, I have an answer. People do not have an answer. At least I have one. I don't know if it's correct, but I have an answer. The sample treated with hydrogen had a higher dopant concentration. If the dopant concentration is higher, the width of the depletion region are smaller, and if the width of the depletion region is smaller, the channeling is higher. So I conclude that channeling is important. We cannot just ignore channeling, right? Okay. So I have to go. How do I eliminate this? Yeah, I want to open the other one. I'm lost with this. Sorry. I went faster than I thought. plus 4. Okay. Okay, thank you. So we go back to our picture that I have shown many times. Yeah? Can everything occur at the surface? Well, apparently not. We can say, people say that all we observe are changes just in the height of the barrel. Yeah? Is this? Yeah. No. And this one. Okay. Can everything explain in changes in the barrel height? And the answer to that, according to experiments, the answer is no. Yeah? Because we made samples with the same barrel height, and we don't measure the same conductivity. Yeah? We have seen this, we have seen this, we have seen this. Well, so we have measured band bending directly from photoemission. Yeah, again the same picture. The barrel height is the same, but what we have changed is the width of that through these measurements. Okay. Now I'm going to add another piece of information, another evidence, yeah, which is the capacitance. What would you expect? Okay, I would expect this is as a function of frequency, how the capacitance of the sample, yeah, behaves. Essentially, all these shapes are very complicated, and then due to traps, the sample is full of traps, and it's going to show very high capacitance of that. But people agree that at frequencies in the order of 1 megahertz, yeah, the capacitance is due only to the capacitance due to the interfaces, yeah, to the Schottky barriers. So what we have to look essentially here is the capacitance here. Yeah? So initially, we don't have ABC here, forgot about that. Okay. Initially, we measure what the capacitance is to this sample preparing oxygen, and we see a large capacitance at this. Okay, this is the original. Okay, this is the original. This is say we measure a low capacitance. Sorry, a large capacitance. This is the original. A large capacitance. So this could be this could depend on the width of the depletion region. If the depletion regions, that is are smaller, the larger the capacitance. But if the whole thing is depleted, we only have the capacitance due to the bulk. It was going to be much lower. So as we heat it up, yeah, as we heat it up, the total capacitance decreases, yeah, and it shows a very low value. And when we heat it up again, we recover about we recover what the original we had. So how that can happen? Well, this could happen only if the whole grain becomes completely depleted of carriers, yeah, because Schottky barriers should present regularly very high capacitance. So this could be strong evidence that something is going on. And what is going on? What is going on that we have indiffusion of carriers, indiffusion of oxygen, yeah, producing that the whole grain is depleted of grains, is depleted of carriers, yeah, and in that case the capacitance drops abruptly, yeah. Do you understand that? No. I did explain it well? No. When we have a Schottky barrier, as the Schottky barrier is narrower, yeah, the distance between is like a capacitance of plates. It's like the plates are closer one to the other one. See? Yes, as the doping increases, it's like the distance between the plates is smaller. If that's the case, the capacitance is high. But if we have indiffusion of carriers, the width of depletion is wider, then it's similar to capacitance with plates which are farther away one from each other, and the capacitance decreases. This is what we observe here. The capacitance changes after the thermal treatment. And if that is the case, it's telling me that we have an indiffusion of oxygen, which is annihilating the oxygen vacancies and then producing the capacitance, right? People, if you don't agree that, we cannot explain this. I didn't find another explanation for this, or no one ever gave me an explanation for this above this one, or the one I have just given you. So we made some calculations. Yeah, here we have the substrate. This is the detail of the substrate. See that the distance here is about 1 millimeter. And essentially, even though we have something complicated here, we can think that we have two plates. This is not like this, that is like this. Yeah, there's a capacitance of two plates which are parallel, but not like this, but like this, as shown in here. Yeah, we have here one metallic, the other metallic separated. So, and the capacitance of two plates which are parallel to each other is given that this complicated formula. It's not so simple as the capacitance of two plates, one against the other one. So essentially we could calculate the capacitance of this thing, and from the surface that capacitance should be very small, about less than 3 picofarads. Yeah. Well, before the deposition of the sensing film, we found a capacitance of 12 picofarads. Yeah, and this is much more than the previous one, but here we have the metals and we have the substrate, which was alumina. So the main contribution was of the alumina, where the metal was deposited. So we calculated the capacitance of the alumina, yeah, which was in the substrate. And those calculations, here is the reference, we determined the capacitance in this order, about 11 picofarads. So it was fine. Eventually what we are measuring before our film, our sensing film, was essentially due to the substrate. That was the capacitance we were measuring. But after the sensing film, yeah, was measured, we measured after the position of the sensing film, we measured about 24 picofarads. So in that way, we determined that the difference, which is about 12, 13 picofarads, is the capacitance of the film we just added. And if that is the case, we could determine the permittivity, which we found the value 12.3. Amazingly, in the literature, the relative permittivity for the tin oxide is 12.4. So we are quite, even though we make many approximations, this works quite well. So the measurements we have been making indicates that everything works well. We have tin oxide, and the permittivity is that corresponding to tin oxide. And this implies that the grains are completely bare. Yeah, because if we have Schottky barriers, the permittivity should be much higher, not that of the bulk of the tin oxide. After the treatments, when we have the larger dopant concentration, the capacity increases 5 times. Yeah, and if the capacity increases so much, yeah, the only answer to that is that the dopant concentration had to be increased. We form Schottky barriers, yeah, and then the total capacity should be much higher than that for the bulk. And if we make it just a simple one-dimension approximation, yeah, the ratio between the film the duration of the two cases should be related to the size of the grain divided twice the width of the depletion region. Yeah, this is very easy to calculate. That is, the part of has a bulk property within the grain. You have to take the whole thing minus the two sizes of the width of the depletion regions. So, making these numbers, yeah, we could calculate the width of the depletion region, and if we know the width of the depletion region, we took taking a reasonable value for the band bending, which is about 0.7 eV. Yeah, we can calculate the doping concentration, and the doping concentration we found when the sample is treated, so we have a high density of oxygen vacancies, reaches a value of about 10 to 25 per cubic meter, which is a reasonable value. People agree with that. So the conclusions of all this is a whole paper, it's very long to explain, it's not easy. But the conclusion of this is, look, you do something to the sample, increase the temperature under oxygen atmosphere or under vacuum, and you can change the dopant concentration to the point where the capacitance changes. Why the capacitance changes? It changes because when you have a low dopant concentration, the sample is completely depleted, and what you are measuring is the bulk permittivity, because you don't have barriers. But when we have barriers, the capacity increases a lot because the distance, yeah, between the plates is like this. The distance between plates should be much shorter because the region which is a bulk property is like a short circuit. So the equivalent distance between the plates, you have to take out the regions without conducting. It's like putting the electric with a metal. So you have a metallic region, is like reducing the distance. Yeah, it's the similar effect. So the capacitance has to increase because the effective distance between the plates is much smaller. And this is what we observe. When we have Schottky barriers, we develop regions which are conducting, and these regions which are conducting are short circuits for the capacitance, and it's an equivalent of reducing the distance between the plates. And that's why we measure a capacitance increase of a factor of 5. And this increase in the capacitance is a clear evidence that we are changing the dopant concentration. And how can we change the dopant concentration in this material? Well, we have to reduce increases. We have to increase the number of the density of oxygen vacancies. And if we want to decrease it, we have to decrease the density of oxygen vacancies. And how the oxygen vacancies change? Well, they change because we have to in-diffuse oxygen or out-diffuse oxygen. This is the only way of doing it. So that is taking place. Yeah. Okay, so again, if we have larger grains, yeah, this is what we expect to happen. If the dopant concentration decreases, the width of the depletion region increases, but essentially we arrive to this. Yeah, we expect the capacitance changes because we have a different region with the bulk properties. And in the case of small grains, yeah, essentially this is going to be depleted of carriers, and the whole thing is going to be depleted, and then the capacitance is going to be much lower. Yeah? Okay. Here you have what's going on in 3 dimensions. Maybe it's clear. This is in 1 dimension. This is a region in the bulk. The center of the grain behaves like a bulk. And this is the width of the depletion regions. Everything is fine. This is the height, the barrier height. So in this direction we have oxygen diffusion. If oxygen diffuses, the dopant concentration decreases, the width of the depletion regions increase, and we can have at this point where the grain becomes completely depleted. And if we go up with the oxygen diffusion, the doping is going to be reduced more and more, so the band bending is going to be smaller because we have no room to the Schottky barrier to develop, and the whole grain will remain completely depleted of colors, right? So the work function, another point. The work function, we said, is essentially the energy needed from Fermi level, yeah, to take an electron to the vacuum level. And so the work function has two terms. Has this chi, is the electron affinity, plus the distance between the EC and EF, is the bottom of the conduction band to the Fermi level. Well, in a semiconductor, the work function can change because of two reasons. Because it can be because this EC minus EF changes, or because the electron affinity changes, right? So how can the work function can be measured using photoemission? Well, it's not so difficult. You have to measure where the Fermi level is and see what is the low kinetic energy cutoff. From here to here, we have a range where the electrons can be extracted from the crystal. That is, you send H nu, you send the photons with an energy H nu, and you have to reduce from there the work function, yeah, because electrons can be ejected from here to there, but from the total energy of the photon, part of that energy is used to extract the electrons from the solid. So the total width in energy of the electrons you can measure are H nu, which is the energy we are using, minus the energy needed to extract the electrons. So if you measure that, which comes from the Fermi level, yeah, to the lower kinetic energy cutoff in photoemission, this distance, yeah, is going to be the H nu, yeah, minus the work function. So and this is the width. This should be the other way, and then we can extract from there the work function. Yeah. What I'm saying that H nu is the width in energy of energy we can measure minus the work function. Well, from that relationship we extract the work function. Yeah. The work function is going to be all the energy of the photon coming, yeah, impinging on the surface, and we have to subtract what we can measure in photoemission, and that difference is going to be the work function. There is a trick to this. What happens if the work function of the spectrometer is larger than that of the sample? Have anyone here have done this before? No. When you did it, okay. The problem we have here is that you can extract the electron from the sample, but the sample has to go into the spectrometer. And if the work function of the spectrometer is larger than that of the sample, it's not going to do it. Yeah, again, it's not going to get into the spectrometer. If that happens, what we are going to measure is the work function of the spectrometer and not the work function of the sample. To avoid that problem, you have to put a bias into the sample, yeah, increase the energy of the sample. So all the electrons, in that case, all the electrons that go out from the sample can reach the spectrometer. Anyway, the width, this, from the Fermi level to the low kinetic energy cutoff, is going to be the same, yeah. But in that way, you're for sure, you know for sure that all the electrons coming out from the sample can reach the spectrometer. Well, with XPS, we could determine the work function, and our results show a difference of about 0.7 eV. Yeah, 0.7 eV.
between those two types of samples we use. If the electronic affinity does not change, then this difference would represent a difference in band bending. Yeah? But the problem is that simultaneously to this, we found that the band bending is the same because the core levels did not change their position. So the work function changes, but the band bending did not. So the correct interpretation of these experiments is that what is changing is the electronic affinity. I'm telling you this because people have been published many papers saying that measuring the change in work function is a clear proof that the band bending is changing. But the band bending has been checked looking at the core levels, and the core levels don't change position. So what changes very different in these two samples is the electron affinity. Okay, I'm going to many details and things very subtle. I want you to understand the general ideas, yeah, what I'm saying. Well, conclusions of all this. I'm going to end up with this, I think you're well titled. The conductivity measurement cannot be explained if we consider that only depends on the height of the intergranular barriers. That's the main conclusion. Yeah, and why is that? The reason for that is that the current through the intergranular barriers is not only due to thermodynamic conduction, but also through because of tunneling. So the results using XPS indicate that the samples with different conductivities have the same barrier heights. So it cannot be thermionic only. If we consider the preparation of the samples affects the vacancy density, we suppose that is the case. We have proof for that. The observed results arise naturally incorporating the tunnel contribution. And also we have been measuring capacity measurements, and there is a solid evidence that the capacitance changes abruptly. Yeah, and these changes in capacity can be easily understood as a consequence of changes in doping. And there is a change in doping, it's a change in the tunneling contribution. So doping changes simultaneously explain both phenomena we are observing. They explain simultaneously why the conductivity changes and why the capacitance of the sample changes. Okay, this is becoming very much more complex. Yeah, so far we have seen what is known, and these are the things which are under debate. Most people do not agree with what I'm telling you now. Yeah, but I think that considering the tunneling current, explains clearly what's going on. Maybe there is a better answer, but I don't know of any better one. And the measurements using XPS and measuring the capacity of the samples are consistent with that. So everything indicates that we have indiffusion or diffusion of oxygen in the samples, and that is responsible for changing the dopant concentration, and changing the dopant concentration changes the tunneling current, and it changes the capacity of the sample. Yeah, and everything matches, everything makes sense. Okay, so not everything can be explained saying that it's a surface phenomena, with all you are changing what's going on the surface. There are changes inside of the grains. Right? So this is much more complicated than typical studies in materials and electronics, where the dopant concentration is always the same. You decide what the concentration has to be. Yeah, and you take ask a guy, okay, I need silicon with this type of doping, and I want it to be N-type, and with 10 to the 17 per centimeter cubic of phosphorus. Okay, here's the device, the material. And you have the material with that doping concentration.
Well, here that is not the case. The dopant, you have no idea what the dopant concentration is, and also it can change. Yeah, and this is very confusing for everybody. And this is why so many people are studying these things for years, have been studying these things for years, and we don't agree on the results. Okay, just today's talk has been much more complicated and difficult. These are unknown things, yeah. But I want you to have the flavor for all this, and this is why so many people continue studying these things, because they're complicated. So what do we want as researchers? Things are not completely very easy because we will know the answer, and we don't want things terribly complicated and complex because we are never going to find an answer. We like things in between, really. So things difficult, so that things that we can solve. Okay, that was a joke in part. Okay, thank you for your attention for today.
Okay, guys, so we will start the second half of the topic for today. So I think the last couple of days we have been talking mostly about a basis or a background in solid state physics, and then Professor Celso also talked about intrinsic semiconductors, extrinsic semiconductors, and then we also did some tutorials. So today when Professor Celso started talking about gas sensors in a polycrystalline essentially metal oxide system, and that's really where you start seeing defects and the role of defects in determining the properties of semiconductors. We didn't really spend a formal session talking about the various kinds of defects, but that's what I wanted to do now. So this is not a tutorial session, this will be mostly a lecture on trying to understand some defects in semiconductors, what role they play. I will also touch upon briefly how we can actually characterize these defects, especially using experimental techniques, because that is something that we do. There are, you will notice that a lot of not contradictions I would say, but still a lot of issues that are unresolved, and even with as simple a system like say zinc oxide, there are still controversies as to why zinc oxide is n-type, what is contributing to it, how do we find out the defect states in zinc oxide, and so on. So again, let's just put one brief slide about what we were doing earlier. So we started off by talking about intrinsic semiconductors. An intrinsic semiconductor is nothing but a pure semiconductor, and more importantly there are no impurities, so it's a single crystal, no grain boundaries and nothing, and no defects. Under these conditions, we can say that the concentration of electrons is equal to the concentration of holes, which is equal to the intrinsic carrier concentration, and of course we even saw the formula for Ni as a function of temperature, and the Fermi level is located close to the center of the gap, right? And this is just the band diagram that shows that Fermi level is at the center. I have a valence band, I have a conduction band, I have a Fermi level, and I have an electron affinity. Of course, in general, this is not true. We can have defects, and normally as metallurgists, when we talk about defects, we talk about 0-dimensional, 1-dimensional, 2-dimensional defects, 3D defects, and so on. Mostly we are going to focus on point defects, which are 0-dimensional defects, and we can see that these point defects can change the carrier concentration. So you can be in a situation where N is not equal to P, and because they change the carrier concentration, they can also change the Fermi level. The same is true if you have an extrinsic semiconductor as well. In the case of an extrinsic semiconductor, again, when we were discussing, we said that these are doped. We add some specific type of impurities to these materials, but there are no general impurities or defects. So only we have dopants, but still it is an ideal material. There are no other defects present in the material. Now because you have an extrinsic semiconductor, you can either have n type, which means more electrons, or you can have p type, which means more holes, and correspondingly the Fermi level will be shifted. Either it is located close to the conduction band or close to the valence band. You can have an extrinsic semiconductor which also has defects, and again these defects can change the carrier concentration. So we have both intrinsic and extrinsic semiconductors. What we were looking so far are ideal, but now we will see that these can be changed because I have point defects in these materials. So we are going to look at point defects or zero dimensional defects. Mostly when we talk about them, you can have a vacancy. So vacancy is I am actually removing atom from its lattice position, or I can have an interstitial where basically I introduce an extra atom into the lattice. Whatever happens, whether you have vacancies or you have interstitials or you have both, this is something that's very important. Ultimately, I cannot have a charged semiconductor. All my positive charges and all my negative charges must be balanced, and this is especially true when you have compound semiconductors or even metal oxide, which is nothing but a compound semiconductor. This electrical neutrality rule must be maintained. Ultimately, all the positive and all the negative charges must balance. So let's look at the types of point defects. So I told you you can have a vacancy. So this is an example of a vacancy where an atom is removed from its position. You can have an interstitial where an extra atom is introduced into the lattice. Whenever we have a vacancy or an interstitial, there is always some distortion of the lattice around this defect. I can have an interstitial of the same type, so that is called a self interstitial. So think about, you have a silicon lattice and I have a silicon interstitial, so that is a self interstitial. And I can also have a substitutional impurity. So you can think of doping as an example of a substitutional impurity defect. There can be other examples as well. So normally we have vacancies or interstitials to be the two broad categories. Let's start with silicon. So because that's a very easy system for us to describe. So let us say I have a silicon lattice. So again we know that silicon has 4 bonds, sp3 hybridization, so there are a tetrahedral arrangement, but we can represent this in 2 dimensions, saying each silicon atom is connected to 4 other atoms, right? So if I have this, then I can essentially mark here. I can have a vacancy in silicon, so one of these atoms is removed, so that represents the vacancy. Usually we say that the extra atom, the atom that is removed, goes to the surface of silicon, right? So we can see here the vacancy atom has essentially jumped to the surface. We have an example where again a vacancy is created, but the extra atom, instead of going to the surface, goes into an interstitial position. So it is still within the bulk of the crystal, but it is in an interstitial position. So that's why we say we have vacancies and self interstitials in silicon. The question of course we want to ask is, how easy is it to create these defects, because that is one of the most important factors that determine whether defects are formed or not. So we can actually calculate what is the equilibrium concentration or the fraction of these interstitials or vacancies. So the important thing to note here is when we talk about interstitials, we are not introducing some other atom, it is still silicon. So we can calculate the equilibrium concentration. Typically we use some sort of an Arrhenius equation. So we will say x is equal to some a exponential minus EA by KT. EA represents the activation energy and A is a pre-exponent term. Together these two terms will tell us what is the concentration of these defects. So if you see here, the first term represents the fraction of interstitials in silicon, and the second term here represents the fraction of vacancies in silicon. The important part I sort of want to highlight is the activation energy. This value is 2.6 electron volts. This value is 3.8. So you can think of the activation energy as how much energy you need to supply to create that particular defect. Lower the activation energy, more easier it is to create the defect. According to this equation, it is easier to create a vacancy in silicon rather than to have a self-interstitial. So it's easier to remove an atom rather than insert an extra atom into the lattice, and that makes sense. If I already have a silicon lattice, trying to push another silicon atom inside, because that is going to lead to greater distortion of the lattice, that's harder. So it's always easier to remove an atom rather than cause interstitial. Since I have these numbers, I can actually calculate what is the concentration of interstitials or vacancies at room temperature. All I have to do is to substitute temperature is 300 and then I can do the math. Let me just erase this. So if I were to do that, if I calculate at room temperature what these numbers are, turns out those numbers are so small that you can sort of treat them to be zero. What this tells us is that at room temperature, the energy to create either a vacancy or an interstitial in silicon is so high that you can treat your silicon as defect free. So that is why especially when it comes to the semiconductor industry, when people use silicon wafers, they have single crystal silicon wafers and they are treated as either pure, so intrinsic wafers, or if they are doped, they are treated as doped extrinsic wafers, but people don't worry about vacancies or interstitials in them. You have to do other things to silicon to actually create these defects. One way to create defects is of course increase temperature. Usually at higher temperature there is more thermal excitation, so it is easier to create defects. So at the melting temperature, so around 1670 Kelvin, you can see that there is a substantial value of these. So this value is no longer 0, the fraction, but there is some finite value. This is as far as silicon goes. Things become slightly more complicated when you have an ionic solid, and especially metal oxides are ionic solids. With silicon it is a covalent bond, so the silicon atoms are anyway neutral. So whether I remove an atom or I put an extra atom, I don't violate the charge neutrality. So everything has still equal positive and negative charge. But if I have an ionic solid, the moment I remove say one of the ions, I will create a charge imbalance, right? So I have to do something to compensate for that. So broadly, when we talk about point defects in ionic solids, we talk about either a Schottky defect or a Frenkel defect. A Schottky defect is one where we have vacancies in both the cationic and the anionic side. So we have both a cation that is removed and an anion that is removed, and this happens in such a way that again the material is completely neutral. In the case of a Frenkel defect, you have a vacancy and the ion that is removed goes into an interstitial position. So you have a vacancy plus an interstitial on either the cationic or the anionic sublattice, and again that ensures that you have charge neutrality. So this is just again a schematic representation of what I've been telling you. So in this particular case I have mx, so mx is my ionic solid, so m plus x minus. So I can remove the metal ion and I can remove the x ion, which is x could usually represents a halogen. So I can remove both of them and that creates a Schottky disorder. Or I can take a metal, remove the metal ion and put it in an interstitial position, and that creates a Frenkel disorder. In both cases charge neutrality is maintained, we are not violating any charges, but both are different kinds of defects. So let's look at Schottky and Frenkel defects in slightly more detail. So this is what I was saying in the previous slide. So I have M, which is the cation, X is the anion. So I have Mx, and just to make life simple we will put this as plus and this as negative. So most common example, if you want to think about it, is NaCl. We know that I have sodium ion, so Na plus and Cl minus. If I remove a sodium ion, if I remove the Na plus or if I remove the M plus, so this is a site which has a positive charge. By removing it, I am actually creating a vacancy that is said to have a negative charge, right? It is the opposite, because I am removing Na plus, that site should actually have plus 1, but now when I remove it, it has 0. So the net effect is 0 minus of plus 1. So I have a cationic vacancy that has a net negative charge. The same way I can remove Cl minus. So once I remove Cl minus, this is a site that should have a minus 1 charge. The moment I remove Cl minus, I have a charge of 0. So the net charge is 0 minus of minus 1. So I have a net positive charge. Does that make sense? Is that clear? Why do we say that the vacancy has an opposite charge to what is being removed? So we have Vm minus that represents the cation vacancy and Vx plus that represents the anion vacancy. We will talk about the notation in just a minute. In the case of a Frenkel defect, you have a vacancy and an interstitial. So again, let us go back to sodium chloride as an example. I remove a sodium ion, not an atom, sorry, I remove a sodium ion. So I have Vm minus, and this sodium ion goes into an interstitial site. So this is a site that has originally 0 because there is nothing there. The moment I put a sodium ion, I have a net charge of plus 1. So I have Mi and plus, that is my interstitial. The same way with anionic vacancy, I have Vx plus, and when this goes as an interstitial, it goes as a negative charge. So either way, I have minus and plus, so I have charges that balance. And even here I have minus and plus, so again I have your charge neutrality. So whether I have a Schottky defect or a Frenkel defect, because I am creating a pair of defects, I am always maintaining the charge neutrality in the system. When it comes to electrical conductivity, this doesn't really should not change the electrical conductivity in any way, because I'm not introducing any new carriers, I'm just moving charges around. You can also have crystals where I have both Schottky and Frenkel. It's not like I can only have Schottky or I can only have Frenkel, but usually depending upon the free energy of formation, whichever is easier to form tends to form. So usually Schottky or Frenkel, one of them will dominate depending upon the energetics of the particular system. Things become more interesting, and especially when it comes to electrical conductivity, if I can have, instead of a pair of defects, I have only a single defect. So I have only a vacancy created on one of the lattice points, or I can have an interstitial. So just to give an example, so let us say I have a perfect semiconductor. So I have a valence band, I have a conduction band, I have some Eg. We already saw that if Eg is very large, then the intrinsic carrier concentration is going to be small. So if I have a metal oxide with Eg as say 3 electron volts or more, the intrinsic carrier concentration in your oxide will be very small, there won't be any conductivity. I can create a vacancy in one of the lattice sites. So in this case we have created Vx plus. So I have created a vacancy on the anionic site. So remember M plus X minus, I remove the X minus and I create a Vx plus. Now one way to of course keep charge neutrality is I also remove an positive ion. So I remove the M plus, that becomes a Schottky defect. Instead of that, I can create this vacancy and have an extra electron that goes to the conduction band. So think about it in the sense that I have Cl minus, I remove the Cl, but the minus charge, which is the extra electron, is jumping to the conduction band. So here again I have charge neutrality because I have a positive ion and I have an electron which has a negative charge. So again I have charge neutrality, but I now have an extra electron that is there in the conduction band, and this extra electron is now available to move when I apply an electric field. So I have increased the charge carrier concentration by creating the defects on the anionic site, right? So by creating the defects on the X site, I have increased the charge carrier concentration. More specifically, I have increased the number of electrons. So what type of semiconductor would this be? It will be an N type, right? So I have started off with a semiconductor that was originally intrinsic. I have not added anything new, I have not added any dopants, but just creating a vacancy, I am actually able to change the semiconductor into an N type. So this becomes an N type semiconductor. How stable this particular situation is depends upon the energetics of the system. Because this is an empty site, that electron in the conduction band can fall down into the defect site. So essentially your defect can go from being ionized to being neutral. And when this happens, when we say that the electron is here, the electron is potentially trapped, it's no longer available for conduction and you haven't really increased the conductivity in a way. Closer this site is to the conduction band, more easier it is for the electron to jump, because there is always thermal energy which you supply, or because the semiconductor is at room temperature, will always allow the electron to jump. So the position of this defect state in the band gap matters. Closer it is to the band edge, which we call a shallow state, the better it is for electrical conductivity. So far okay? Mm-hmm. So there are ways to do it, especially when it comes to how you make your semiconductor. I will try to show you some examples with zinc oxide later on. That's the system that I have worked with. There are other ways to do that as well. Okay. Anything else? So if I can create n-type semiconductor, so let me just erase this. I can also do the same by creating a p-type semiconductor. So in this case, I have a vacancy on the metal side, so Vm minus, and this is Vm minus because an electron from the valence band jumps here. When an electron jumps here, the absence of the electron is nothing but the hole. So I have excess holes in the valence band. So again, this now becomes a p-type semiconductor. I'll write here n-type, so it's just to be consistent. This becomes a p-type semiconductor. Again, the energetics of this particular system matters. So depending upon the energy required to create the defect, it can go back to being neutral. And of course, you can have situations where we have pairs of defects, and then you have charge carriers that are created when you have pairs of defects as well. So normally when it comes to defects, there is a very standard notation that people use to denote them, and this is the Kroger-Wink notation, and this is something that you will come across in multiple textbooks and papers when people talk about defects. So the Kroger-Wink notation essentially is, I have S that stands for species, P stands for position in the crystal, and C stands for charge. So S, P is the subscript and C is the superscript. Depending upon whether the defect is negative, positive or neutral, we have different notations. So you have a hash, you have a dot, or you usually denote as X. Some books will have some minor changes in maybe for the neutral position, but usually this is the accepted convention. So there are various notations. For example, let us say I have a vacancy. Vacancies are usually denoted by V. So V here represents the vacancy. The position in the vacancy could be either in a, say in a metal site, in which case you will say Vm, or it could be in an X site, in which case you have X, and then depending upon the charge created due to the vacancy, you can have positive, negative and so on. And we will see some examples in the coming slides, but again these are various possible defects which are created in the crystal. I think couple of days ago someone was asking about an anti-site defect, so that can also be generated in the Kroger-Wink notation, where anti-site just says that I have a metal that is actually present, a cation that's present in the anionic site, or vice versa. So we will talk about defects, but in the context of say one particular semiconductor which we will choose. I will take zinc oxide just because that is a system that is very widely studied, but there are still some controversies or still some issues that are unresolved, especially as to the electrical conductivity or the nature of electrical conductivity of zinc oxide. I think most people have some sort of an agreement, but there are still some issues that are out there. Now this is the band structure of zinc oxide. We really didn't talk about the band structure in detail, but the main thing I wanted to sort of point out in this diagram is that the 0 here represents the top of the valence band. So this is the top of the valence band, and this valley here represents the bottom of the conduction band. So this is the valence band maximum, so it's called VBM. This is the conduction band minimum, so CBM, and this is the band gap of zinc oxide. the same information here is available in the density of states figure, but just the take home message is that I have a band gap, and the band gap of zinc oxide is somewhere around 3.4 eV. So zinc oxide is a wide band gap semiconductor. It's also a direct band gap semiconductor. Just to show you what direct means, if I go here, I can see that the bottom and the top, so the top of the valence band and the bottom of the conduction band lie in the same value of K. So this is nothing but a K point. When that happens, we call it a direct band gap. If not, it's an indirect band gap semiconductor. So zinc oxide is a wide direct band gap semiconductor. Zinc oxide can actually have various defect states, and interestingly these defects are related to how you actually process the zinc oxide. So let's take the zinc site. I can have interstitial, so my zinc atom can be in interstitial position. So we normally write that by saying zinc, I represents interstitial position. This interstitial can be neutral, so X represents neutral. I can have one electron that is removed, so I have zinc, the dot represents the positive charge, or I can have two electrons removed, so I have a doubly ionized, so two positive charges. So that is nothing but the Kroger-Wink notation. Instead of a zinc interstitial, I can have a zinc vacancy, so I am removing the zinc atom from the lattice. So V represents the vacancy, I am removing the zinc. The vacancy can be neutral, or I can have one negative charge, because now remember originally it was +2, I am removing the zinc there, or I can have two negative charges. So again I can have a neutral vacancy, single, or doubly ionized vacancies. Same way when you talk about oxygen, just like how you did for zinc, you can have oxygen as an interstitial, so oxygen can go into the interstitial positions, or you can have oxygen as a vacancy, so you can have V in the oxygen site. So these are all the possibilities. Of course there are different energetics associated with each of them, and they can also have a pair of defects. So you can also have a defect pair, that's what I said. Because for example I can have a zinc vacancy and an oxygen vacancy, that makes it a Schottky defect, or I can have a zinc vacancy and a zinc interstitial, that makes it a Frenkel defect. Turns out that obviously whatever you do, you need to have charge neutrality. So this means you can have excess electrons. If these excess electrons are in the conduction band, you get n-type, or you have excess holes. If these are in the valence band, you have a p-type material. So people have looked at the band structure of zinc oxide in detail, and this is just one particular diagram which looks at the energetics of the various situations. Turns out that in the case of zinc oxide, the most commonly observed defects are oxygen vacancies, so I am removing an oxygen atom, and zinc interstitial. So these are the ones that are most commonly produced. So if I go back to the previous diagram, an oxygen vacancy essentially says I am removing an oxygen atom from the lattice. So originally it is a site that has -2. The moment I remove oxygen atoms, that particular site has plus. To maintain charge neutrality, I will have then excess electrons in the conduction band. The same way if I have a zinc interstitial, I am introducing some positive charge. To maintain the neutrality, I can again have some electrons that are there in the conduction band. So either way, if I have oxygen vacancies or zinc interstitials, to maintain charge neutrality we have extra electrons in the conduction band. So pure zinc oxide, so it's intrinsic, we are not adding any dopants, because of defects have more electrons than holes, which is why we call zinc oxide to be an n-type semiconductor. These defects will also modify the optical properties, which we will see in a minute. So how do we actually create these oxygen vacancies? So one particular way is, let us say you have zinc oxide, and this is something that we have done in a lab. You can buy commercial zinc oxide powder from any of the vendors. You make a pellet, let us say you compact it, make a pellet. If you heat the pellet in a reducing gas environment, so in an environment where there is no oxygen, but typically a mixture of say hydrogen and argon or hydrogen and nitrogen gas, that will take away some of the oxygen from the zinc oxide, and that would create oxygen vacancies. So one way of creating vacancies is essentially by annealing the sample in different environments. So pure zinc oxide turns out has more electrons than holes, so it's an n-type semiconductor, and by processing it I can also vary the carrier concentrations. If I create more oxygen vacancies, consequently I should have more electrons in the conduction band, which means I must have higher conductivity. If I can create an n-type semiconductor, we can also create a p-type semiconductor, and nickel oxide is a classic example of a p-type semiconductor. If I have pure nickel oxide, we normally say nickel plus 2, but nickel is a metal which can exist in multiple oxidation states, so you can have plus 2 and plus 3 states, and again to maintain charge neutrality you tend to have nickel vacancies. These vacancies, because remember I have a side that is plus, by removing I am actually creating an extra negative charge. To balance that we need more holes. So if I have these nickel vacancies, these are located close to the valence band, and then electrons will go and jump and occupy these states, creating excess holes. So pure nickel oxide, so again this is in pure in the sense we are not doping anything, but nickel oxide is a p-type semiconductor. And if you actually take zinc oxide and nickel oxide and put them together, I have an n-type and I have a p-type, which means I can make a p-n junction, and these are essentially heterojunctions because they are two different materials. An extreme example of creating defects is an amorphous semiconductor. So I think in the beginning of the course, Professor Celso talked about long range and short range order. Whenever we have crystals, we always tend to think of crystals having long range order. So there is a lattice, there is a basis, and atoms are distributed according to that. An amorphous semiconductor is one where we have short range order but not necessarily long range order, and silicon is a classic example of a material that is also used in the amorphous form. So in the case of amorphous silicon, so let's go back and look at crystalline silicon first. So again each silicon atom has 4 bonds, so each silicon is bonded to 4 other silicon atoms. If we break this long range order, we create silicon atoms where not all 4 atoms are connected to others. So we have what are called dangling bonds. So they are essentially silicon atoms with a free electron, which is now available for bonding because I no longer have this periodic arrangement. In many cases these dangling bonds are terminated by hydrogen, so we call these hydrogen terminated bonds, and what happens in silicon is also true in the case of germanium. So silicon or germanium has a tetrahedral coordination. When this is broken, we create these dangling bonds, and usually during processing, just to maintain the stability, they are terminated by hydrogen atoms. How do we make these? Typically we have chemical vapor deposition processes which work at low temperature in order to make amorphous silicon or germanium. these have a very interesting band structure. Normally when we talk about band structure, we have a valence band, we have a conduction band, we have a forbidden region, a region where no energy states are present. But because I have a lot of defect states, so once again I have my valence band, I have my conduction band, and all of these dangling bonds create defect states within the band gap. So this particular region is the band gap. So if you look at the distribution of states in these materials, so this is the valence band maximum, this is the conduction band minimum, it is correctly. Then this region represents the band gap region, where we have a lot of energy states that are available because of these defects. And this changes the nature of electrical conductivity. Normally when we talk about conductivity, we say electrons are moving in the conduction band or holes are moving in the valence band. But because of these defect states, we have what is known as hopping conduction, where electrons jump from one localized defect stage to the other. So we have what is called a hopping conduction in these defect states. More importantly, we say that for these materials, the Fermi level is pinned at the center of the band gap, which means the Fermi level is at the middle, it cannot move because I have a whole bunch of defect states in them. And that will have some implications when you're trying to make junctions. So Professor Celso talked about either a Schottky or an ohmic junction. I cannot really modify the properties of my junction by doping because I already have a lot of defect states which are pinning my Fermi level. So finally, just briefly, how do we characterize some of these defects? We normally use some sort of light interaction with semiconductors. The most commonly used one is nothing but UV visible absorption. As the name implies, you shine light ranging from the UV visible, usually also go up to the near IR region. So the more general term is UV visible NIR. So you shine light through your sample. There's also usually a reference sample, so you can take the difference. In this particular case, the sample is in a liquid, so you can see these cuvettes with liquid in them. So if you make some semiconductor nanocrystals, nanoparticles, you can disperse them in a solvent, and that would be your test sample. You have your plain solvent alone as reference, so you can get a difference signal. But people also do this in the solid state. I can also have a thin film and do these measurements. So when we think about absorption, whenever we shine light on a semiconductor, as long as the energy of the light is greater than the band gap, we say that the light is absorbed and electrons go from the valence to the conduction band, right? So that's the most general picture. Light falls, electrons take that energy and jump to the conduction band, and this happens only when the energy of the photon is greater than the band gap. But more than that, light absorption also follows how the density of states are distributed in the valence and in the conduction band. So this is diagram here. So G of here is nothing but the density of states. This is the band edge. So this is again the valence band maximum and the conduction band minimum. So this represents the band edge. So EC and EV. Beyond EC and EV, whether you have a uniformly or a monotonically increasing density of states, or you have some functionality depending on the semiconductor, that information can also be mapped by the absorption measurements. So okay, so let me just, so here again is an example of gallium arsenide and silicon. So gallium arsenide is a direct band gap semiconductor. So the absorption edge is a lot more straighter. It has a band gap of around 1.43. Silicon has a lower band gap, but it is an indirect band gap semiconductor, so the absorption coefficient increases more gradually. Using UV visible absorption, we can also calculate the band gap of the semiconductor. Most papers will refer to this as the optical gap or the optical band gap, because it relates to the band gap that is measured by optical absorption. So in this particular case, the sample is scanned over a wavelength range, and then we have essentially, let me see if I can get this, yeah, essentially some sort of a function. So in this particular case, alpha is the absorption coefficient, h mu is the energy, n depends upon whether I have a direct or an indirect band gap semiconductor, and that is just given by h mu minus Eg. So we make a plot of alpha h mu versus mu, and the x intercept gives us the band gap. So this is a particular example for zinc oxide. We also have another example for, say, nickel oxide, where this is a plot of the absorption. From the absorption you get alpha, and then you make a plot of alpha h nu square versus energy, and then you can get the slope, on from the slope the intercept, and the intercept gives you the band gap. So most people commonly use UV visible absorption along with this plot, with this top plot, in order to measure the band gap of a material. Another technique that is commonly used, especially to study defects, is photoluminescence. So again, the idea is I have a source. Typically the source is a monochromatic source, so it has a single wavelength, and you have a wavelength that is, or an energy that is larger than the band gap. So you excite, and then you look at the light that is emitted from your semiconductor. So this usually works if I have a direct band gap semiconductor. So you have light absorption at a single wavelength, and then you measure the light that is emitted as a function of wavelength, and using that you will have some information about the energy transitions or the radiative transitions in your particular material. So you can have a band to band transition. So you shine light, you absorb light, electron goes and falls back from conduction to the valence band. So that is your band to band transition, which gives you the band gap. You can have defects that are present. So you can have defect transitions, so that if they are radiative, that is again something that you can measure. And especially when people do photoluminescence at low temperature, so that thermal effects are minimized, you can even identify multiple defect states that are present in the material. The last technique again is Raman spectroscopy, which people again use a lot, especially to study defects. So here again you have a monochromatic light source, and then you look at the shift, or the shift in the energy or the frequency of the light source when it interacts with a sample. Usually we have what is called a Stokes shift, where the frequency or the energy reduces, and this can again be used to identify defects. So depending upon the particular sample you have and the conditions, the Raman spectroscopy can be used in order to characterize the types of defects that are present in your sample. So just to sort of end this with an example, I just thought I'll pick something up from what we did a few years ago. So we were making essentially zinc oxide nanoparticles by a chemical reduction technique. So you start off with zinc nitrate, react it with sodium hydroxide, we do a dropwise addition that precipitates zinc hydroxide, and because you are doing dropwise addition, we can actually get nanoparticles. When I heat the zinc hydroxide, the water essentially escapes, leaving behind zinc oxide. So we can get zinc oxide nanoparticles, and the X-ray diffraction tells us that this is crystalline. So we don't have to worry about amorphous states. This is crystalline zinc oxide. So how do we characterize this? We look at the absorbance. So we do UV visible absorption. Zinc oxide, I told you earlier, is a wide band gap semiconductor, so it tends to absorb in the UV region, and then the absorbance is low. And based on that, we can essentially look at the band gap of the material, and the band gap works out to be, if I remember right, this is approximately like 3.2 eV, which is slightly lower than the bulk band gap, but it's possible because there are some defects in the material, and that defects are actually captured by PL. So when you do photoluminescence, you see there are two bands. This band at around 380 nanometers corresponds to the band edge emission. So this corresponds to the band gap, and especially for zinc oxide, people see a lot of this. You see a very wide band in the visible region, usually around the green region, and this is a defect related emission. It's usually associated with oxygen vacancies. If you were to do the same experiment at low temperature, this typical white band, you can actually resolve it into multiple individual bands, and based on the energies you can assign it to the different defect states. So optical spectroscopy is actually a really good tool to measure and characterize some of the defects that are present in semiconductors. And this is important because these defects can affect the electrical properties. So from understanding the defects, you can go and understand the electrical properties. Right. So I'll stop here. Are there any questions related to the material? Yeah.
So is this optical band gap and electronic band gap are same?
Technically they are the same, but usually we, if for example, if we have some shallow defects close to the band gap, the optical band gap will also take into account these defects, while electronic band gap technically is from valence band to conduction band, so these defect states would not come into picture. So that's why we always use the word optical band gap, just to say that it can also include some shallow defects that are there close to the band edges.
That means optical band gap value is lesser than electronic.
Yeah, it will be, if you have the defect state, it will be lesser than the electronic band gap. So if you see here, this value is 3.2, while typically zinc oxide's band gap is 3.4. That's what people get from DFT calculation. So this difference is probably because of the defects that are there in the material. Yeah.
How can we measure the actual electronic band gap?
So it's again, for example, let us say you have a material which you know is defect free, then your optical band gap is the same as the electronic band gap. That's probably one way to go about doing that. Any other way to measure electronic band gap? So I'm not sure. Yeah, that's another way. So you look at how resistance changes as a function of temperature. From those plots, you can extract the band gap. Yeah. Thanks.
Yeah, in Raman spectroscopy, how is it possible to find out the defects?
So usually you look at the Raman peaks. So of course, any defects in Raman spectroscopy they have to be Raman active. So what we normally do is we look at the peaks, and then there are enough literature, especially related to zinc oxide, that says these lines correspond to these particular phonons, and these phonons would get modified because of the presence of defects. So it's not direct in the way you're looking at the phonon spectrum and then trying to correlate that to the defects. So either you must have prior studies, or people have done the systematic studies, so you have the data, or you have to generate those data, probably again through some calculation routes.
In the case of bulk form, defect may be very less. So it completely depends on intensity count.
It depends on intensity counts, and Raman is usually more, people say Raman is surface active, so you may not be able to capture the defects in the bulk. It's more for defects that are closer to the surface. That's correct.
Cathodoluminescence can be used for characterization of defect states.
Cathodoluminescence.
What is cathodoluminescence? You'll have to remind me now. We might have done that in the course, right? Like it was taught that it is used for semiconductor microelectronics industry for characterization. I'm not remembering the whole process. So, like the word So
Basically, luminescence always means emission of light. So photoluminescence means I shine light and that creates carriers, and that degradation leads to light. Electroluminescence means I inject charge carriers, and when these charge carriers recombine, that's going to give me light. Let's see what would cathodoluminescence mean. So I'm trying to break it down from first principles. Yeah, I know there is a cathodoluminescence spectroscopy usually associated with SEM, where people do use it for looking at defects, but something I'll have to probably look at before I can answer that. But I do know there is a spectroscopy tool that is associated with when people do SEM. They can also do that, probably just to see which areas of samples light up, and then based on that they can look at some defect states. But right now, off the top of my head, I don't remember how CL works. Questions?
Adding doping or removing the.
Usually doping is better because you can always control. Defects are much harder to control, and you cannot increase defect concentration very high because there's always some thermodynamic equilibrium that has to be maintained. So especially when you want to change charge carrier concentration, doping is better. Okay. All right, if there are no further questions, we'll stop here, and we're close to 12 o'clock. So tomorrow we'll have a slightly different schedule from today. We will still meet at 9, the time will not change, but tomorrow I will start, we'll talk a bit about transparent semiconductors. So I will go for the first 1 hour, then we'll just have a photo session. It will be nice to get a group photo of everyone who's participated in the GIAN course. So we'll arrange that tomorrow. Hopefully we can do it outside, provided there is no rain. If not, we will do it here. So either way, we'll have a class from 9 to 10 where I will start out, and then we'll have a photo session, then we will have a coffee break, and then maybe at around 10:30, 10:40, Professor Celso will take over, and then he will continue the rest of the session, right? So please do make sure you're all here tomorrow morning for the whole thing, but at least for the first hour, so we can also get you in the photo session. All right, nothing else. We'll see you guys tomorrow. Thank you.